In this section, we are going to talk about generics and traits. Generics are going to allow us to have stand-in types for our concrete types. Traits are going to allow us to represent a capability that can be implemented in on many different types. So, without further ado, let's jump right into it. Wouldn't it be nice to be able to create code that can operate on values of many different types? Luckily we can, and it is through generics. Generics are abstract stand-ins for concrete types. We've already used generics in this course, and it was in the last section when talking about options. So let's take a look at how we can use generics. So to start off, let's create a struct, and we'll call it point. And then we'll assign it a generic of type T, which can be any type. And then inside we'll have X, which is T, and then Y, which is also T. So currently, whatever value we pass in to X and Y, they're going to have to be the same type. So for example, I32, and then that's what T will be, so therefore this also needs to be I32. So let's create a point, and we'll call it point, and then X, we'll just name it 5.0, so we're going to make it a float, and we'll just do 5.0 again. And so that's perfectly valid. So we can also, if we wanted to for whatever reason, wanted our point to be characters, well, we can say X, and then we can also say Y. And that's also valid. So we can see that T can be of any type that we want it to be. It's just a placeholder until we're able to figure out what type is needed. So currently what we cannot do is mix and match these. So we cannot go character for one and then a float for another. But we actually can fix that, and we can allow it to do that. So we can add in another generic, which is going to be a U in this case, and then add in a U there. And now we are able to have two different types in here. So now we're able to do this. Oh, I don't want that. So now we can have a character and a float in here because we're able to accept two different types. And truly, that's really all there is to it for generics. Generics are just going to be placeholders until we're able to fill in a concrete type. And generics are really powerful in this sense because it allows us to be flexible and make our code a lot more modular for handling different concrete types, such as I32 or a float, Booleans, whatever it might be. So it just allows us to have a lot of flexibility, which we will be able to see as we continue on in this course. A trait represents a capability, something that a type can do, and can be shared with other types. We can use traits to define shared behavior in an abstract way. So let's create a trait just to see how it's done. So all we have to do is use the trait keyword followed by the name we want our trait to be. So we're going to create an overview trait, and in this trait we're going to define a function called overview that is going to refer to itself and return a string. And then to use this trait, we can actually implement it in with a type. So let's create a struct, and we're going to call it course. And then in here we're going to have a headline, which is a string, and then the author, which is also a string. And then I'm going to go ahead and create another course, which is going to implement the same two things. So in here, what we're going to do is we're going to implement overview for course, and we're going to say fn overview self. We're going to return a string, and then in here we're going to say we're just going to format out, and then we just want to do self dot author and self dot headline. So just something really easy for us to do. And then we want to do the same thing for another course. So as you can see, we were able to implement the overview trait for two different types, which is exactly what we want to be able to do with the trait and exactly what the definition of a trait is. But something that we can do is we can actually have a default implementation for our trait. So in here, we're going to say we have a string from, and then we want it to say this is a Rust course. So now if we come down here, let's create a couple of our structs, and we'll say let course1 equal to course, and then we're going to have our headline as a string from headline, and then our author is a string from Tyler. And then we want to do the same thing again, except this time we want it to be for another course. Another course, and we'll say another headline and another Tyler. Alright, so good. So we have no errors there so far. So let's create a print and say course1 dot overview. So we're calling the trait that we implemented. And then in here, let's say course2 dot overview. And now let's run it. So we see Tyler headline, which is what we implemented up here for course, and then we also see another Tyler, another headline, which is what we the values that we gave down here. So now how can we use our default thing? Because we currently are overriding it. So let's just go ahead and delete all of this. So now we just say implement overview for course, and we took out our implementation for it. So now if we run it, we actually see this is a Rust course, which is the default implementation for it. And that's how traits work. So let's see what else that we can do with traits in the coming lectures. We can pass traits as parameters as well. In the earlier examples, we implemented the trait overview for both course and another course. So let's create a function that's going to call the overview method from its item parameter. So the first thing we need to do is create that function. We're going to give it the item parameter that's going to have a reference to the overview implementation. And then in here, we're just going to print out overview and then item.overview. So since we already have these two types created that implement the overview method, we can call them. So we'll call course1, and of course we need to pass it by reference. And then we can also do this for course2. So we run it, And we see this is a Rust course, which is course 1, and also the default implementation. And then we have our modified course, which is another tiler, another headline. So awesome. So that's working good. But we can actually simplify the function. And what we can do is come in here and say type T of overview. And then we can just change all of this right here to just say a reference to type T. And it's the same exact thing. So the first way we did it is convenient and makes for more concise code in simple cases, whereas what we have implemented now can express more complexity a little bit more clearly. Also, the implementation overview works for straightforward cases. So what I'm referring to now is what we did in the earlier case. So let me go back to that. So the implement overview, let's get rid of the error. The implement overview works for straightforward cases, but is actually just shorthand for a trait bounds. So let's look at some different trait bounds. And I'm just going to have all these commented in. That way we can just kind of see everything side by side. So the first one is going to be if we had the overview function, we had item 1, and it was, implementing in the overview trait, and then item 2 also implements the overview trait. So this allows item 1 and item 2 to be of different types, but we can force them to be of the same type if we wanted to. And that's where the method that we just had comes into play. So we can say overview again, but this time T of overview. And now it's going to be item 1 and T, and then item 2 and T as well. So again, these are the same thing, but this one can have different types, and this one we are making them have to be the same type. And then the last thing we can do is we can have multiple trait bounds, and this is done this way. So we created our function again, we're passing in item 1, and we're going to implement in overview, and then plus, and then our other trait. So plus another trait allows us to have multiple trait bounds. And then just to keep everything uniform, if we wanted to see this in the other way, it would be T overview plus another trait. And then we have item 1 and T, item 2 and T. And that's going to make them have to be of the same type. So with all of that, I just wanted to show you some extra functionality we can use traits for, and I hope it all makes sense. I know we have learned a lot about generics and traits so far in this section, so just take a second to make sure you fully understand everything before continuing on to the next lecture, where we will start talking about utility traits. In this lecture, we're going to start talking about utility traits. And utility traits are a grab bag of various traits from the standard library that have enough of an impact on the way Rust is written that it's important for us to be familiar with them. So the first one that we're going to look at is the drop trait. And we've heard the word drop be used kind of throughout this course. And when we talk about dropping in Rust, we are referring to the freeing of the resources the value is using. Drops occur in a number of situations, such as when a variable goes out of scope, at the end of an expression, removing elements from a vector, and the list goes on and on. Luckily, Rust almost always will handle this for us, but it is an important trait to know, so let's look at how we can use it. So we'll piggyback off of our struct course, and what we'll do is we'll implement drop for course. And then we're going to have the drop function, which is going to contain a mutable reference to the self. And then in here, just to demonstrate how it works, we'll say we're dropping, and then we'll just say self.author. So now when we come down here, we can manually call this ourselves, and we could say drop course1, because that is what used our course struct. And now if we run it, we'll see that it says dropping Tyler. So we manually called this drop trait, and we manually freed up our resources. But we could delete this line and rerun this and see that it still calls dropping Tyler, because here is where course 1 went out of scope. And so it called our implementation of drop, which we told to, hey, print out dropping Tyler and then free up the resources. So that is what the drop trait is. And now let's go look at a couple more, starting off with what the clone trait is. The clone trait is for types that can make copies of themselves. For this to work, it needs to construct an independent copy using the self keyword, and then return it. A clone's definition is as what's followed. So we have our trait clone, which also implements the sized trait, and then we have a couple of methods associated with it. Cloning a value typically means allocating copies of anything it owns, which can make clones very time and memory expensive. Just imagine taking a vector of strings and cloning it. Every string inside the vector would also be cloned, so as you can expect, a clone can indeed be very expensive. The types like i32 and Boolean implement clone, but other things such as mutexes, which we will talk about in the concurrency section, do not. Another trait we talked about a little earlier on in this course is copy, but now we're able to talk about it a little bit more in depth and as to what is allowed to implement a copy. Simple types like i32 that don't own any resources can be a copy type. A type is copy if it implements trait copy and then clone, so what we're seeing here. Rust is going to allow a type to implement copy only if a shallow byte-for-byte copy is all it needs. This means that any type that owns any other resources, like a heap buffer or operating system handles, cannot implement copy. There are two ways that we can implement a copy. We can say derive, copy and clone, or we can implement copy for our type, in this case it's a struct, and then implement clone for our struct. Remember though, making a type copy places extra restrictions on our type, so it's important to consider the pros and cons prior to doing so. The from and into traits are going to allow us to perform conversions on a value of one type and then return it as another. So the definition for into is right here. So we're going to take ourself and then return a value of type t. And then from is very similar, but we're going to go from a value of type t and then return ourself to it. So from is going to serve as a generic constructor for producing an instance of a type from some other single value. When we define our own types, if it has single argument constructors, we should write them as implementations of from the appropriate types. Rust is friendly and will give us the corresponding into implementations. So there is also a try from and a try into. So imagine trying to implement from an integer of 64 for an I32. Any other case would result in information being lost, right? Because we're going from 64 bits down to 32. So we're going to truncate it in half, resulting in lost bits. Try from and try into are naturally very similar to from and into, but try from and try into are the error catchers. So if we come down here and look at its required methods, we can see that we're having a result returned of self and self error. And we'll be able to make more sense of this when we learn about errors in the coming lectures. But I just wanted to introduce this to you. So the methods try from and try into are going to give us a result. And then we can choose what to do in the case we are thrown an exception, aka an error. And again, we will cover error handling more in a couple of sections, but I just wanted to show this to you as it's going to allow us to extend the simplicity of from and into. And then with all these utility traits, and there are more of them, I just wanted to introduce to you their concepts, so as you begin to see them later in this course, we're able to make better sense of them. Operating overloading is how we can make our own types support arithmetic. In order to show these, we are going to show how to add coordinates together of any type. So the first thing we need to do is bring in add into scope. And it is in standard ops add. So now we're going to create our struct of a point with a generic type and assign 2 fields in here, all of the type T. So now we can implement add for point, and then in here we're going to do something we haven't done yet, but we're going to say where T of add output equals T, and I'll break all this down in a second. And now fn add self, right hand side, self, return self. Okay, so we added this where in here, and what that is going to do is it's going to restrict T to types that can be added to themselves, yielding another T value. So in my example, what I'm gonna want to do is take 2 coordinates. So we'll say let coord equals point of x 5.0 and then y 5.0, and then we'll copy and paste this to make it go quicker, and we'll just add 1 and 2. So when I was talking about restricting T to types that can be added to themselves, I'm just saying like we want to add a float to a float already. That way we keep this example nice and simple, just to really show what we're trying to do here, which is implement adding points, which is our custom type. So now let's implement the logic for adding here. So we're going to say point, and then we're going to have x is going to be equal to self.x, so the left hand side of the equation. So just to show this, we're going to say let sum equals coord plus coord2. So this coord is left hand side and this coord2 is right hand side. So we're going to say self.x, which is left hand side, plus self.y, which is going to be the right hand side. And then also the same thing for y, self.y for left hand side plus right hand side self.y. And that's all we have to do. So now let's just go ahead and print this out. And we're going to need to use the debug form of printing, and we want to print out the sum. Now, since we haven't implemented in how to print out this, we actually need to derive in. So we're going to use derive and then debug, and it went ahead and added that in for me so I can take it out. So now we'll be able to print this out using the debug formatter. So when we cargo run it, value used here after a move, and that is because I needed it to be right hand side. There we go. Now we should be good. Oh, right hand side X. And now we see we have printed out a point with 6 as the X coordinate and Y as the 7 coordinate, which that looks correct. So what we were able to do here was use the add trait to implement arithmetic for our own unique type, which was a point. But this logic we can apply to all arithmetic operators. It was just something I wanted to show you how we could use the add in order to implement our own operations for our custom type. I hope you enjoyed this section on traits and generics. We are now going to go over to the solution for the assignment for this section. Question 1 was modify the solution to the section 4 assignment by creating a trait that has the setMPG, setColor, and setTopSpeed methods. Then create a motorcycle struct with the same fields as the car struct, and those fields were MPG, color, and top speed. Now we are going to implement our trait on both the car and the motorcycle struct, and then print out the results to confirm a working solution. So the first thing that we will do is take our solution from the section 4 assignment and paste it in. That way we are set back up with where we were at. And now we want to create a motorcycle struct. So I'm going to copy and paste the car struct and just rename it motorcycle and leave the fields the same. We are now going to create a trait, and I'm going to call this properties, since these are properties of a motorcycle and a car. And now we can take our methods. So I'm just going to go ahead and copy and paste all of these up here, and we can do that. So now we have our trait successfully set up. So now we want to implement our trait for each of our structs. So we will say impl properties for car, and we will leave our implementation right here the same for car, and now we will also do the same for motorcycle. And now we can create our motorcycle struct, and we can also go ahead and now assign it our set values. So we'll say our motorcycle gets better miles to the gallon, we have a black color, and our top speed is 150, and then we want our default color, we'll have it as green. So now we want to run it, and we see we have printed out, I need to motorcycle, I guess this is where, motorcycle here, I was going a little too quickly, motorcycle, motorcycle, and now we can print out both of our structs now that we have them successfully set up. And we see that we now have our new motorcycle struct printing out the appropriate fields above. So that is one possible solution to question 1. Question 2 is create a simple print function that uses generic type T. This generic T will need to implement the standard format debug depending on the values you pass in. Our function takes one parameter that is of type T, and then our function will print out the value that is passed in. So we can create our function called print that is of type T, and it's going to take one parameter, which we will call value, and we need to now implement in the standard format debug, so that way we are able to print out our value that is of type T. So now we can print out value. And so if we come down here, we can call our print function on a wide variety of things. So we'll create a vec and we'll pass in values 1, 2, and 3. We'll call our print function on a string slice. We'll call our print function on a string from string number 2. And then lastly, we just want to print out a simple integer, so we'll print out 10. And now if we run this, we see that we are able to successfully print out 4 different types of values thanks to the ability that we gain when we use generics. So I hope you were able to follow along and compare your solutions to mine. If you have any questions about any of the solutions, or maybe your solution that differs from mine, please feel free to ask them in the Q&A section.